In this lesson, we are going to be talking about Newton's second law. So by the end of the lesson, you should be able to explain what Newton's second law is, and you should be able to calculate the different components from the equation F equals ma. So what is Newton's second law? Well, Newton's second law is the law of force. It says that a force that is acting on an object will cause the object to move in the direction of the force. So, like when you're a little kid and you are pulling your younger sibling around in the wagon, well, you are applying a force by pulling the wagon, which is then causing the wagon to go in the direction that you're pulling it. So, when we calculate Newton's second law, we use the equation F equals ma. And that stands for force equals mass times acceleration. And we know what mass is, we know what acceleration is, and we've learned what force is. And so the typical units for force is newtons, and breaking down newtons to what it actually is it's kilograms times meters per second squared, which makes sense because we know that mass is generally in kilograms, and we know that acceleration is meters per second squared. So when you multiply those together, you get newtons. So let's do some practice with the F equals ma equation. So if a 1,000 kilogram car is accelerated at 2 meters per second squared, what is the force that the engine produces? Well, we're using the F equals ma equation. We know our mass is 1,000 kilograms. And we know that our acceleration is 2 meters per second squared. So we don't have to do any rearranging for this equation at all because we're looking for force in this case. So our equation is going to look like this. And we know that 1,000 times 2, well, that means that's 2,000. And our units is newtons. So this car produces 2,000 newtons of force to get this 1,000 kilogram car to accelerate at 2 meters per second squared. So let's try this one. We've got a frog that leaps from its resting position at the lake's bank onto a lily pad. Well, if the mass of the frog is 0.5 kilograms and the acceleration of the leap is 3 meters per second squared, what is the force that the frog exerts on the lake's bank when it's leaping? So again, we're using our F equals ma equation, and we are looking for force, so we don't have to rearrange the equation. And we know that our mass is 0.5 kilograms. We know that our acceleration is 3 meters per second squared. So just plug that into the equation, 0.5 times 3. Well, this should give us a force of 1.5 newtons. All right, so we've used many equations before, so using this equation, probably not too difficult for you. But let's talk about the mass and acceleration relationship. Well, so if we have an object that has more mass, we know that it's going to cause the acceleration to be less because it's going to be pretty hard for that thing to accelerate, and vice versa. So if something has a very small mass, it can accelerate pretty quickly. But if this object has more mass, well, now that we are talking about forces, we need to know that if it has more mass, well, then it's going to require more force in order to get that object to accelerate, and vice versa. If it has less mass, it's going to require less force, which then causes it to accelerate a lot faster. So the force and the mass for an object are relatable. The more force, the more mass. The more mass, the more force. The less mass, the less force. And so the mass and force have a direct relationship. They both increase. And the mass and force have an inverse relationship with acceleration. The larger the number of the mass and the force, the smaller the number of the acceleration, and vice versa. So, but what about falling objects? So if we have two different objects with different masses and they are dropped at the same time, what do you think is going to happen? Well, many things could happen.
Jack holds both balls above his head and then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time.
I expect them to both land at the same time.
Same time. Same time.
Well, I think they both will. This one to hit the ground first. However, they would actually both hit the ground at the same time.
Yeah. Why is that?
Science. Yeah, science.
Now the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed. From this height, yeah, pretty much. Just a constant speed all the way down.
Speed? Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar.
In terms of gravitational pull, they're both at the same and they'll fall at the same rate. I'm not like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull and you've told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier and has more gravitational pull. But when I drop them, then they get equal to gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes, but scientifically speaking, no.
The gravitational force on both these balls are the same.
Okay.
The gravitational force on both of these balls is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe it should be more on this, simply for the fact that this is heavier, and just intuition tells me that it should be more, but after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
No, you don't.
I swear. I am not trying to mess with you. So,
Like in real life?
in real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yep, see?
Same time.
I would say the force on the medicine ball is like a lot more because it's got a lot more weight, it's got a lot more mass, but it's got a lot more inertia.
Yeah. Oh.
You guys remember that, right? It's got a lot of resistance to acceleration, so it takes more force to get it accelerating at the same rate as this ball. And that's why they accelerate at the same rate. Thank you guys so much for playing along. I appreciate that.
Sorry,
Thanks,
Jared.
Jazz. That's all right.
So what you saw in that video was that the balls had two different masses. One was a medicine ball and one was a basketball. But when he dropped them, they fell and hit the ground at the same time. And this has to do with talking about more mass, more force. The medicine ball had a larger mass, which caused it to need a larger force for it to accelerate at the same rate as the basketball that had a smaller mass, which needed a smaller force. So we saw they fall at the same rate. And generally when you drop something, the acceleration that the object is going to fall at is 9.8 meters per second squared, which is gravity. So looking at this picture, you can kind of see how the math works out for the acceleration to be the same. We've got this elephant here that weighs 1,000 kilograms. It's falling with a force of 10,000 newtons, and it ends up having the acceleration of 10 meters per second squared. And then you've got this tiny little person who weighs 1 kilogram, is falling at 10 newtons, but still has the acceleration of 10 meters per second squared. So anytime something falls, if they have different masses, they're still going to drop at the same time. And they're still going to hit the ground at the same time. All because of the relationship to force and mass. So now let's just do a little bit of recap. We know that Newton's second law is the law of force. We know that it states that the force that is applied to an object will cause it to move in the same direction as the force. We know the equation for Newton's second law is F equals ma, or force equals mass times acceleration. We know that the typical units for this equation is newtons, and we symbolize that as N. We know that the breakdown of that equation is kilograms times meter per second squared. We know that the more mass an object has, the more force is required to move the object, which causes the acceleration to be smaller, and vice versa. And if we drop two objects of different masses, they will fall at the same rate and hit the ground at the same exact time. So this wraps up the lesson for today. Make sure you write down any questions you have in your journal, like always. If you feel they're very important, please email me and text me, and I will get back to you. Otherwise, have a great day.